Welcome to week 5. Things are moving right along, almost near the end of the semester. Okay, we're going to be jumping in talking about graphs, okay, in C++. So week 5 are learning outcomes, explain the shortest path algorithm and their applications, solve network flow problems using standard techniques, construct minimum spanning trees, apply greedy strategies to solve optimization problems, implement dynamic programming solutions to complex problems, understand and apply randomized algorithms appropriately. So some interesting stuff here. It is basically the backbone, if you think about it, on how GPS works. And it's one of the things, GPS and navigation. Now, and looking at it here, I want to bring this up because this basically is kind of the crux of what are connecting things. And here we're talking about graph representation. And why would you want to have to worry about how I represent the graph? Here's an adjacent lists are space efficient for sparse graphs. Adjacent matrices allow fast edge existence checks. So if I can quickly know whether a edge is connected to another edge very quickly, that can help me in my process of finding a path from point A to point B. So one of the things in graph representation, anywhere you see a 1, there's a connection. Anywhere you see a 0, it's not. From this information, basically I'm being the computer, I can quickly find out whether I can get from point A to point Z. And if I can, what is the best way to do that? So this is kind of the adjacency list and adjacency matrix. Again, we're going to be going into this in a lot more detail in class, but wanted you to kind of look at and kind of realize that that edge connection, that adjacency matrix, explains a lot as to what we're going to be looking at in this particular week. Okay, so here, the week objectives, the shortest path, the network flow, minimal spanning tree, greedy algorithms, dynamic programming, randomized algorithms. Okay, those are the things that we'll be touching as it relates to week 5 and graphing. Okay, so graph algorithms, the shortest path algorithm, find the least cost path between two nodes. I'm going to point A, point Z, get me there the cheapest way. Okay, maximize flow from source to sink. Okay, that's a network flow. MST, connect all nodes with a minimum cost, minimum spanning tree. Okay, what is the minimum spanning tree that I can use in order to get the least cost of getting from point A to point B? Greedy, okay, make the best choice of each step. Rather than looking at whether this choice is going to affect 3 choices down, what you're looking at is you're saying, right now, what is my best choice? And that's a greedy algorithm, okay? Dynamic programming, okay, break problems into overlapping subproblems and randomize, use randomize to improve performance. Okay, and we'll talk about each one of these and what they mean to this whole concept of shortest path. So here, vocabulary, shortest path, the minimum cost between two nodes. Network, the movement flow from one network from the source to the sink, where I'm starting to where I want to end up. Minimum spanning tree, subset of edges that connect all nodes with the minimum total weight, no cycles. Greedy algorithm that builds a solution by making the best local choice at each step. Dynamic programming, a method of solving problems by combining solutions to overlapping subproblems. And randomize an algorithm that uses random choices to solve problems, often improving speed. We'll be talking about each one of these. Why it matters, we talked about GPS, communication networks, infrastructure design, optimization in business, bioinformatics in science, security and cryptography, those who've taken my cryptography course, so you'll always have some of that. Okay. But here's are some of the matters. This is the thing that basically path-oriented processing. This is the construct of what our main purposes that we'll be looking at week 5. Everyday examples, finding the fastest route on a map app, minimizing water supply from reservoirs, connecting communications with minimal costs, pricing best deals with limited budget, okay, solving puzzles with overlapping steps, and Monte Carlo simulations. Okay, got two dice and you're rolling the dice, and what's the probability that you're going to get a certain number. So these are kind of the things again we'll be deep diving in on the Thursday in class. But I want to kind of give you an idea, kind of a focus. Okay, where are we? What are we looking at? The underlying concept that we want to get is how do we get to traverse a path from point A to point B. Okay, kind of in summary. So here, Dijkstra, the shortest path algorithm. We're not going to go through it here, but you may be able to use this as far as when we start getting into explaining line by line what's happening. Okay, but here's how that would look in C++. The minimum spanning tree, Kustra. This is the C++ implementation for that. And dynamic programming, Fibonacci. Okay. We did some Fibonacci in our last homework assignment, or some before that, but here is the C++ for doing Fibonacci. Here, code walkthrough from the shortest path algorithm. This kind of breaks it down. We will be going through this, kind of step by step, showing at each step how things are different in the table. Okay, so we'll be there. This is basically a walkthrough that as you go through step 0 through 4, what's happening as far as getting that information and developing the shortest path that I want to be able to partake. Okay, Dijkstra will always picks the shortest unvisited node next. Okay, we'll get into that detail. Common mistakes, ignoring edge weights. Always consider weights in graphs. Unweighted assumptions lead to wrong answers. We'll discuss what does that mean. What is an edge weight? Why does it make a difference? Increased base condition. DP solutions need to correct base cases in order to avoid wrong results. Okay, not updating properly, failing to relax edges or update. This is given incorrect paths. Again, going through the process, not seeing that something happened and not correcting it. Okay. Using wrong data structures, choosing the wrong structure, for example, queue instead of priority. We basically said this all throughout the class. Okay, all throughout the class, we need to pick the correct structure. So we'll kind of deep dive on more in that in week 5 as to, okay, which structure should I be using? Okay, as far as the knowledge questions, I'm expecting you to basically be prepared for in case I give you a quiz. What is the difference between Dijkstra and Bellman-Ford algorithms? And by the way, just want to make sure and I'll kind of reference this. This is going to be a closed book quiz. Okay, not open book. Okay, when should you use Kustra versus Prim? What is the goal of a Maxwell problem? How does dynamic programming differ from greedy algorithms? What is the difference between Monte Carlo and Las Vegas algorithms? Again, study these questions. It's kind of an overview, high level, 5,000 foot of this particular week. Okay, and we'll be kind of delving in more detail to kind of give the underlying reasons of how these processes work. Okay, thank you everyone, and we will see you in week 6, okay, before we delve into our project. Have a good one. Bye.